Okay, I lost it there for a second. So we divide by the 294.24 by the 2 pi r of a, and we get 15.6 revolutions of a. That's how far a is going to travel. Now, for the time, we know it's constant, so we're going to use our equations from kinematics. So we know 1/2 times the angular acceleration, t squared, is what we're going to use for constant acceleration. Now, what we type into here is we know from up here that we have this constant acceleration term. So we're going to drop that into here, and then the time requirement, 5 seconds squared, because that's how long it's going to take us to get there. That's going to give us 31.43 radians. So, radians, 31.43 radians. So that's the amount of rotations required to achieve a uniform velocity. And what we can do now is to figure out our total radians that we travel for moving up the 20 feet. We take the total distance traveled divided by the 3 inches to get our total amount of radians traveled. So once we figured out our total amount of radians traveled for the 20 feet, we can subtract the ones required to get to that uniform velocity, and that gives us a difference of 66.65 radians. So now what we're going to do is we're going to take this amount and we're going to plug it into our equation that we did earlier, or just divide it by our total amount of radians per second traveled, or velocity, and that's going to give us a certain amount of time. And now we add that time to the 5 seconds it took to get to that constant acceleration, constant velocity, and then that will give us our total time to complete this whole cycle. So we have 66.65 radians. We're going to divide that by the 12.57 radians of what our radians per second squared. No, sorry, radians per second. That's our angular acceleration up here, angular velocity. So we're going to divide the 66.65. That's the difference from when it's traveling uniformly, by our constant velocity, angular velocity, and that's going to be 5.302 seconds. So we know it takes 5 seconds to get to the constant velocity, and we know it takes 5.3 seconds to finish the rest of the cycle. So combined, that gives us a time requirement of 10.302 seconds. Okay, so now we can move on to the next problem. Okay, so this is our next problem, 15.4. We have a disk that moves in the XY plane. Now, we know that the y component of A, its velocity, is negative 7 meters per second. The x component of B is negative 7.4 meters per second, and the x component of C is negative 1.4 meters per second. We want to determine the angular velocity of the disk, the whole thing, and the velocity of point B. So, we have 3 relationships here. We have the velocity of A has an x component and a y component. Velocity of B also has x component and y component. They all have x components and y components. And, okay, sorry for the jump there. So we know that velocity of A, velocity at point A is the component velocity at v sub 0 plus the velocity of A to 0. Cool. And we know that the velocity of A to 0 is the angular velocity crossed with the radius from A to 0. And we know that the velocity at point B is velocity at v0, and then again v to 0. So what we can do is we can actually sub in some of our knowns into this. We go to here, v sub A is equal to v of point 0, the origin, plus v sub A to 0, which again is this term right here, which is going to be omega k minus 0.6 I. Sorry, that x was confusing. That's a cross. Omega k cross negative 0.6 I. And what is that saying here? So what we're saying is that's d sub 0, and the angular velocity here crossed with the radius here, that's 600 millimeters. It's going downwards in the I direction. Here we go. I'm looking at it this way. I'm like, that's not I. This way. So, yeah. I'm confirming, making sure I didn't make a mistake on this one. Did I make a mistake?